the efficiency to conclude that ANFIS is better than the particle swarm optimization method.
Okay, but to me, for ANFIS, you need a computer. Your system is
learning
with a microprocessor, with a learning, with memory, and for PSO you just need a device, discrete devices. Is right?
Yes.
So
yes.
The comparison, do you think that it's better to use this micro computing system for effectiveness of the solution?
Yes.
So there is a difference between the two.
Yes.
Regarding the cost, the total cost of the system.
Right. Yes. You have some criteria for evaluating the performance of the system. You were right when you say that the response the ANFIS need a machine learning to his process, but with space or you don't need them. So in this paper, I just use three criteria to evaluate the performance of these two methods.
Okay, one last suggestion. I think that the ANFIS will be more sensitive to parameters modification and the PSO not. You have to look at this question. The sensibility against the parameter variations.
Yes.
Okay, thank you very much.
Thank you very much, Mr. Dakio, for your valuable suggestions. And thank you very much, Mr. Nadaye, for your presentation. I would quickly share this screen for the certification of participation. Congratulations, Mr. Nadaye, for certification.
Thank you.
Okay, so that is the final presentation of this session. We are through with the virtual session 2, and there is a last presentation for the remaining of the today's conference. So that is it from my side. Thank you very much to the organization and organizers for allowing me the opportunity to session the chair, and all the audiences and presenters to be a part of this conference. Thank you very much.
Thank you to chair this session. It was very well organized.
Thank you.
Let me remind you that all the certificates have been sent to the presenters email today, so including the last presenter now. So today certificates has already been distributed. So now we have another session, first tutorial. Dr. Philip Asset from University of Icsmartgrid in UK. His title of the tutorial is the voltage source converter based high voltage transmission system. We have not assigned a chair for this session because Graham will chair his own tutorial, and then we leave the microphone to Graham. Please, Dr. Graham, your turn.
Okay, just a minute. And how can I request okay, just let me share straightforward.
So we can hear your voice and your picture, but there is no presentation in the screen.
Okay, just a minute. Yeah, just be with me. Yeah, okay, just a minute.
Now we can see your screen, yes.
Oh, can you see me now?
You can start now.
Okay, can you see now my presentation?
We can see your screen, but not it is not
No.
it's only your
Not yet.
No.
Not yet.
Not yet. Yeah.
computer.
Oh, okay, then just let me go back. Stop sharing. Okay, maybe I share.
Change window.
Just a minute. I think this one, yeah. Can you see this one?
Yes, that's great.
Yes.
That's
Good.
Okay, my name is Grant Philip Adam. My presentation today about VSC-based HVDC transmission systems. And I would like to thank Professor Kolak for inviting me, and hopefully, actually, I will try to go as fast as I can. And the outline of my presentations, first I'll give brief overview of voltage converter for HVDC application. And then I'll introduce modular multi-level converters. And afterward, I'll go to mixed cells, MMC, briefly, and enhanced modular multi-level converter. And if there is time, I'll go to the last part, which is, I think, is relevant to the smart grid, which is energy storage assisted power converters. And also, just to be aware, I will try to keep my presentation slightly high level, just because people from different background, I don't want to go to so complex mathematics, but at least to focus in the key concepts. Let's go. Conventional two-level voltage converter. This is the basic VSC initially used for machine drives, and in late 90s introduced to high voltage DC. It is simple. It is simple. It is simple 6 pulse bridge with IGBTs, and we have in this side we have capacitance, and the AC side we have filter. And it's called voltage source because it switches constant DC voltage to produce variable AC voltage. So the input voltage must be fixed. Then the voltage here in the AC side will be pulse. Then after filtering, we'll have pure AC voltage. And the key point from these basic topologies are, first of all, the peak of the AC voltage, the peak of the fundamental AC voltage will be produced at this point is defined by these expressions, which is half times modulation index times VDC, and the modulation index can vary from 0 to 1.27, and the peak of the line and the VDC must remain above the peak of the line-to-line voltage to have control operation. This is necessary voltage to prevent the AC voltage imposed by the grid to turn these diodes uncontrolled to end position. And also, the VDC must be constant to prevent any cross-coupling between AC and DC side. And fundamentally, these converters switch DC voltage, produce voltage like that. The voltage is not sinusoidal, but fundamentally the voltage is sinusoidal. So after you pass this square wave into this filtering, at this side, we'll see have this nice sinusoidal voltage. So if we consider one phase leg of these two-level converters, we have upper switch and lower switch. This switch must operate in complementary manner. So if you turn this one off, this one must be on. If this one on, this one must be off. So when we turn this one on, we connect this point to the VDC if the ground is here. So the voltage at this point is VDC over 2. And when you turn this one off and this one on, this point become here. And so the voltage at this point become minus VDC. And through PWM, we produce something like that. Then with fundamental, we need. So if we define the modulation index or modulation signals in this form, the voltage, the fundamental voltage at this point would be defined like this. And this clearly, and this like this. And this clearly shows that this converter operate like amplifier. You can see like half VDC multiplied by this one give you the fundamental voltage at this point. And when we operate in the grid, then actually we control power by manipulating this modulation index and this angle, or the angle of this voltage relative to the grid voltage, as we have here. So this is the first diagram actually depict how the VSC control active or reactive power. So if we define the grid as a reference, so if we control the grid voltage here, the vector of the grid voltage here, to lead the grid voltage, so the power flow will be from the converter toward the grid. If the vector lag the grid voltage, the power flow will be from the grid toward the converter. And changing the magnitude of the voltage here will also define the amount of Q. So based on these equations, if we change, for example, here, this point corresponding to leading power factor in this region, this one unit power factor. At this point, you operate at 0 Q in this component equal to this component, so Q0 at this point. And at this point here, this one is bigger than that, so this one is positive, so the reactive power will be from the converter to the grid. In this situation, the reactive power, because this one is smaller than the grid voltage, the reactive power will be from the grid toward the AC, toward the converter. And modulation method for HVDC. And in brief, transfer modulation allow the VSC to control active and reactive power independently, which is, as I explained, by manipulating the phase and magnitudes of its terminal relative to the grid voltage, which is these two quantities. So the independent control, not because of DQ, as people may mention in the papers, but because we have 2 degrees of freedoms. This is why we can control the active reactive power of VSC independent. While in LCC, because we only control firing angle, this is why P and Q were coupled. And also the PWM also help the VSC to suppress the harmonic far away from the baseband. Baseband, if you have here, if you see here, this is spectrum, this is the fundamental. So the integer number of fundamental, we call them baseband frequency. So you can see here, there's no second, there's no third, there's no fifth. So all this baseband is clear when we use PWM. The first group of harmonics we'll have in VSC, which is switching frequency and sidebands. And sometimes we call them interharmonics in power systems. So the higher the switching frequency, the far this group from that, then it's easier to filter them out and so on. And also, when we use sinusoidal PWM, which is the initial PWM exists, the maximum peak AC voltage we can produce at the converter terminals is half VDC because the modulation index range from 0 to 1. When we inject such harmonics, we can extend that range to 1.115. So we have 15% extra AC voltage we can produce, and this corresponding to more active power we can produce, or we can operate converter a slightly higher voltage, we can reduce the current in the devices, so we can reduce the losses in the converter. And the other approach is selective harmonic eliminations, which offer similar feature like selective harmonic and their source harmonic injections, but it is much better than this option, because this one is very, very, very good approach, it may not be interesting in terms of research-wise, but industrially is very important because it only creates switching instance which eliminate harmonics, while these two create extra switching actions of no use. This is why, and also instead of eliminating harmonics, you can just optimize to meet the grid code. And here is the basic structure of two-terminal VSC HVDC transmission systems. And in this, at least one of the converter must control active power, and the other one must control DC voltage directly or indirectly. But this is the basic thing, so you have to define a DC voltage directly. The converter that control active power vary the VDC up and down. They're up and down a constant voltage defined by this by the controller controlling VDC. In that way, we control the active power and so on. And the feature of conventional two-level converter in HVDC applications is we can reverse the power by change of the current directions. And this is very important, especially in multi-terminal DC application, because it's easy to keep all the DC voltage fixed. You just change the current direction, so each power flow in the other converter remain independent. And also, DC cable withstand unipolar DC voltage. This make also, as mentioned, and also actually make the DC cable for VSC cheaper. And also, it has the black start and 4-quadrant operation. The black start, which actually it can perform the same function of simplex machines in case of blackout of a system. If this system is blacked out, you can use this converter to restart the power in this system. And also, 4-quadrant operation, which means actually it can sync and source active and reactive power. So you can transfer power in these directions or this direction, and the same to Q in this direction and in these directions. But remember, the reactive power doesn't go to DC. Only active power who can change to DC power. But the reactive power can be circulated within the converter and its AC side. So there is no link, because you can find in some literature, there is no link between this capacitor and reactive power. And also it's resilient to symmetrical and asymmetrical AC fault, as we will see later. And also it has the simplicity of the control and the power circuits compared to the latest topology. But its limitation, it has high losses, around 3%. Yes, 3% in low voltage is not a big issue, but 3% in 1,000 megawatt is 30 megawatt. So it's significant in high power applications. But this limitation now is likely addressed in new topologies, and in very weak AC grids with ACR in the limit of 1 and 1.5, its active power transfer capability diminishes rapidly and exhibit poor controllability. But this is also not limited to conventional VSC. This is to all VSC. And one of the problem in HVDC, because now the highest IGBT is 6.5. If you need to operate this one at 300 kilovolt, you have to series large number of devices. But this technology exists, but it's not widely available within the industry. And also is vulnerable to DC fault, because during DC fault, this capacitor also discharge current, then the fault current become significantly higher to handle. From here, we go to modern multi-level converters. I'll jump straight forward to modular multi-level converter. And just to recap, this is the basic structure of the two-level converter, which is initially here series IGBTs. In this one here, in the MMC, we just replace this series IGBT by the series cells. These series cells can be half-bridge cells or full-bridge cells. So we go, and also these capacitance, we cancel them, we distribute them in these cells. And also the filter, we get rid of this filter, also we add them into the cells. So from here, we evolve to this structure, which is MMC. And in the conventional two-level converter, this is, as I mentioned earlier, this is the type of voltage we produce. Now we produce very good approximation of sine waveform, which we can convert as it exactly sine waveform with nearly zero harmonics if we increase the number of these cells. And here is some of the few cells, and this is some of the type of cells. This one, the half-bridge cells, I would call it half-bridge unipolar cells because it only generates voltage with single polarity, which is either 0 or V cell, and its operation is simple. It has two switches. This, like in two-level, this switches operate in complementary. When this one is on, this one is off. When this one off, this one is on. When this switch SM is on, this point is short circuit, so zero voltage is produced at this point. When this switch is off and this one is on, this point is connected to this capacitor, so the voltage at this point will be equal to the voltage across these capacitors. So by controlling them in a manner, we can produce this nice waveform. And similar strategy here, but here we produce 3 voltage wave there, but here we produce 3 voltage levels, and this kind of cells we call full bridge symmetrical bipolar because it produces positive and negative and 0. And we call this one 3-level cells, with symmetrical output, because the positive, because the number of voltage level with positive polarity equal to the voltage number with negative polarity. And I'll explain also the implication of these types of cells in the performance and control range of the MMC, which is here. And just to recap, this is simple depiction. This is the half-bridge unipolar cells. This is other type of unipolar cells, but instead of 2-level cells, it can be multi-level cells. This can be either flank capacitor or neutral current clamp cells. And this is just simple full bridge cells, which is symmetrical bipolar cells. And if we connect the full bridge in series with the half bridge cells, we create another cells. We call it hybrid, but this produce a symmetrical bipolar because the positive, in the positive we have two voltage levels, and with negative only one voltage. So asymmetrical, and this is also another example of symmetrical bipolar cells, which is with similar functionality to like the half bridge, like the full bridge cells. And the implication of this type of cells you can see in the control range, of the VSC. When we look in the top part here, between 0 and VDC nominal here, this region from here to here, this is the control range of the MMC with unipolar cells, regardless if 2-level cells or multi-level cells. So the half bridge, and 3-level cells, flank capacitor and neutral plate, the control range will be from here to here. And when we use a full bridge cell, which is symmetrical bipolar cells, the control range can go from here to here. And also we can exceed the VDC. This means we can operate with positive DC voltage here at this point, or we can operate with negative DC voltage at this point. So this actually makes the VSC with full bridge cells well fit to operate with LCC type, because in LCC type, if you want to reverse the power flow, you have to reverse the DC voltage. While if you came with the middleware, which is such as the cell with asymmetrical bipolar. So you extend the control range, but only from here to here. And you can create a lot of things in between. And this is just simple illustration, the implication of different type of cells in the control range of the, and also the advantage of MMC with bipolar cells, if symmetrical and asymmetrical, it can recreate any DC voltage. As I mentioned before, if you have MMC with unipolar cells, either this or this, your control range remain the same like the conventional two-level converter, which the DC voltage always has to be positive, and the minimum DC voltage has to be above the peak of the line-to-line voltage at this side. While if you have an MMC with bipolar cell, symmetrical or asymmetrical, you break that rule. So the DC voltage can go from the rated to 0, and still you can control the active or reactive power between the converter and the current flow between converter and the AC grid. And here is a simple example for the voltage across the upper and lower arms. And you can see here the upper arm and lower arm of each first leg of the MMC operate in complementary manner if you see based on these equations. And I'll explain later. And in brief, the key point here, each arm of the MMC must be able to block the full VDC. So if you add the cell capacitance of all cells in each arm must be at least equal to VDC, and at each instant, the both arm of the upper and lower arm must be able to recreate VDC. This way, the V upper arm plus the arm equal to VDC. And if you have the MMC with unipolar cell like half bridge or this one here, the V line to line is limited by this, which is √3 over √2 times half modulation index times VDC, and the maximum modulation index for with such amount of injections equal to 2 over √3. While if you use MMC with bipolar cells, you are there. Your maximum line-to-line voltage, you can see here, is no longer linked to VDC like in this one here. It's linked to the sum of the capacitor voltage because you have the capacity to regulate this voltage higher than VDC like here. So we call this one overmodulation. So you can choose, but this has to come at expense. You have to expose your device slightly at higher voltage to be able to go above the VDC. Just to capture the key point here, the MMC generate output voltage with low harmonics and dV by dt. This is important because this has implication on the design of transformer. So with large number of cells, you can use simple transmission transformer, which is cheaper. While if you have fewer cells, you have to use a slightly expensive transformer to be able to cope with the switching action of the IGBT and the stress due to the switching. And also, it has low switching losses and noise because the devices operate at low frequency, and high modularity actually made the maintenance much easier, and also made continuous operations much easier. What does it mean? So if you go here, for example, if you lose one of the cells here, you can just bypass these cells and continue to operate. So what you can do, you can just add extra cells as a redundant in case if something happens, you just bypass the default cells and you continue to operate, which is much difficult if you have conventional two-level converter. And also the key point of the MMC with bipolar cells, they are resilient to DC fault, as I mentioned. Which means you can block DC fault, or you can control the fault current during DC fault, while also still retaining the control over reactive power. And And also during pole to ground, you can also continue to operate with half of the power and half of the DC voltage without exposing a DC cable to extra voltage stress. And unlike the conventional VSC or unlike the half bridge, here you have new degree of freedom because, as I mentioned earlier, in VSC you can reverse the power by change of the current polarity. While here, if you have bipolar, you have the capacity to reverse the power flow either by change of the current polarity of DC voltage polarity. I will show this one later. And also its operating range extend beyond that of conventional VSC and half bridge MMC. As I mentioned, you can operate with positive DC voltage or negative DC voltage. But the main shortcomings of the MMC with bipolar cells is the higher conversion losses. Why? Because if you see here, in the half bridge, you have only one device conduction pass. Here you have two device conduction pass. This is one of the problems with the bipolar cells. And a little bit, and here is the here is the basics equation that govern the operation principle of the MMC. And here we can drive the expression for the voltage, for the arm voltage of the MMC like that by considering this loop from here to this point. So the voltage across the upper arm can be expressed like that. And similarly, the lower arm. And this alpha, we call it DC modulation index. We define it like this. And this is the AC modulation index, which can be defined by this. So this is linked to the amount of AC voltage will be generated at this point, and this component is related to the amount of DC voltage can be seen in the DC side. And we have two main loops. We have differential mode loops and we have common mode loops. So from here, when we subtract the upper arm from the lower arm, we produce the output AC voltage, which is like that, which is the voltage here. So the voltage appear at the output is the difference between the upper and lower arm. So we call them differential mode voltage, and the output current represent the difference between the upper and lower arm. So also we call them differential mode current. So in this figure here, so this blue line here and here the differential mode loop, while the common mode is if you add the upper and lower arm voltage will give us the VDC, and if you add the upper and lower arm divided by 2 will give us the common mode current. This the current will flow through the red loop. This we call common mode loop. And these two loops actually give the MMC a lot of flexibility, and also plus some of the existing similarity with conventional two-level VSC systems. So the key point here, the P and Q control is realized by a similar way of the conventional VSC, which by controlling the M and delta, as I explained before. While you can see here the power exchange slightly here more complicated. And the MMC use the AC current of the arm to exchange power between the converter arm and AC side, while using the DC component of the arm. You can see the arm current has two components. It has this component, but this component here, we call it common mode current, and we have this AC, and here, this is the AC current, which is half of the output current. You can see here, it uses this DC component of the arm current to exchange the power between the arms and DC side. So you need some kind of power balance between the AC and DC side. So the amount of AC current, the amount of the AC current and this kind of arm have expression. I think you can find them somewhere, maybe later. And the second harmonic capacitor voltage ripple caused by cross modulations in the MMC arms tend to drive a new current, which is we call it circulating current, which is this current component we call here is H. And the adverse impact of this current, it increase the ripple in the capacitor. So you will need bigger capacitor to have lower ripple, which is meet the requirement, which is around 10%. This is one of the consequences of that, and also it increases the losses. And so the countermeasure, actually, there is control. You have to develop a controller which inject small second order harmonic voltage into the common mode loop to be able to suppress this current in order to reduce the capacitor size and also to reduce the losses. And also you can see here this component, even this component doesn't leak to the output circuit, it only circulate in this red pass, while these components only go to the output side. So it doesn't leak to the DC side. And opportunities, and I want to provide here also more context. The MMC vary a DC modulation index, which is alpha D, to achieve the following: to decouple the cell capacitor voltage from the DC link voltage, and which facilitate cell capacitor to be regulated at VDC over at least VDC over N, not necessary. So I can regulate this one at any value I choose. So this allows me actually to add more cells if I want than needed, and I can keep the voltage of these cells at the required value. So if I lose some cells, I can just bypass the faulty cells and continue to operate without any difficulty. And in the MMC, with symmetrical and asymmetrical cells, the AC voltage synthesis also could be decoupled from the DC link voltage. Just to capture in unipolar cells, as I mentioned, this one vary narrow one. So the AC voltage is linked to VDC, while in these two, in MMC with symmetrical asymmetrical the type of cells, the AC voltage is defined based on this. So the higher I regulate this voltage, the higher the AC voltage I can produce. And the MMC require dedicated intercell capacitor voltage balancings that ensure equal cell capacitor voltages in each arm. Why that? The cell has to be regulated because the IGBT will see the voltage across the capacitor. So the overvoltage across the cell capacitor will be seen by the IGBT or by the semiconductor as overvoltage. So you can damage your semiconductor devices. This is why the capacitor voltage balancing is very important components of the MMC. You can find too many publications in this area. And fundamentally, there is two approach for balancing the capacity in the MMC, which is the initial one was proposed originally by Marquette, which is we call it actually sorting based approach, and the second approach, which is proposed by Professor Akagi, which is distributed capacitor voltage balancing. These are the two, and I'll explain this one later, and the merits of each approach. And also we will need a vertical capacitor voltage balancings, which allow the MMC to ensure the upper and lower arm must have equal DC voltage. And this is important, especially actually in real applications, because of the tolerances of the capacitance and inductance of real components. You have to have this controller to ensure the upper arm have the same voltage as the lower arm to prevent appearance of the DC component in the output AC voltage. And this is normally achieved by forcing the voltage across the capacitor. I'll call it the capacitor voltage sum of the upper arm and capacitor of the lower voltage must be equal to 0 to ensure actually have equal voltage, equal capacitor voltage sum across the upper and lower arm. And this controller inject small fundamental AC voltage into the common mode lobes. While we recognize its benefits, it increases the risk also of fundamental current ripple in the DC voltage. So this has to be there. But this will happen in extreme cases, which I may explain later if I have time. Yeah. And here is a generic control systems for the MMC, which is this part is similar to conventional two-level converter, which is in the outer loop. You have either DC voltage controller or active power, and here you have AC voltage or active power. So if you use DQ, if your D axis is aligned with the voltage, which means any voltage components in line with the voltage is power components, and any voltage which is 90 degrees with the voltage the active power components. So in that case, in the D axis, in the outer loop, I have DC voltage or active power, and in the active power axis, we have and the output I have AC voltage or active power. Here I have DQ, positive and negative sequence controller, and I have here circuit current controllers, and I have here vertical and horizontal voltage controllers. And this is to ensure one of these to ensure the voltage impulse across the three first leg of the MMC equal, and the other one ensure, as I explained, the DC voltage across the upper arm equal to the lower arm voltage. And in the MMC with bipolar cells, fault current control will be needed to quickly adjust the DC component of the modulation there, of the modulation index or function. In the alternative implementation, which is I just added here, this is also another implementations of the MMC controller, which is slightly different than the other one. I will not go into more detail because it's so complicated here. And here is a sample result here. Just a minute. Okay. And here you can see here, this is the first voltage of the MMC with only 20 cells. How look nice? It's only 20 cells. So if you have 200 cells, you produce pure sinusoidal voltage. And this is the line-to-line voltage, and this is the capacitor voltage. And this is the voltage across the arm. And this is very important here. Let me zoom in here. And this one here, this is the upper arm and lower arm, and the lower arm current. You can see here in this case, deliberately there is no circuit current controller. You can see here the upper arm and lower arm include second order harmonics, and the red one here is a differential mode current, which is the upper arm minus the lower arm. You can see even though the upper and lower arm were distorted, but a differential is still clean sinusoidal, which is resemble this, and the common mode, which actually the upper arm plus the lower arm divided by 2, which is give you this one, the black one. You can see here it's not DC, it's DC plus second order harmonics. You can see clearly from here. And this one here is the same case. We just include here circuit current controller. You can see here now here it's not perfectly eliminated, but you can see here the upper and lower arm. If I zoom here, if you see here, you can see here it's clear. The upper and lower arm is slightly much better, and the common mode become almost DC. But still there is some remnant second harmonic on them, while the differential mode remain unaffected. And when we go here, this is the case with large number of cells, which is with 300 cells, or 301 cells per arm. You can see here, this is the phase voltage. It almost looks sinusoidal. And you can see here, this is the upper and lower arm. And you can see this is the common mode current, almost DC. So we can summarize as follows. The MMC with reduced number of cells per arm, like for example 20 cells, as in this example, generate nearly perfect sinusoidal phase and line voltage. As the number of cells per MMC arm increases, its output voltage that converges toward ideal sinusoidal, as you can see from here. So with nearly zero harmonics, though in this case, you can see in this case, there is no need at all for any kind of filter. And also the inherent second order harmonics in the MMC cell capacitor drives circuit current as we saw there. And also the output current in the current is the differential mode current, which is as we explained just in the previous one here. I will not go here. And also here, you can see here. And here, this is the relationship between the output current and the DC components of the arm current, or just simply equal to one side of the DC. So the DC current is split into three into arm. Or you can link it to the output current by this expression. And while the common mode current, this one comprised of two components, which is DC and second order harmonics, as explained, and it circulates only within the MMC in the common loop, as explained earlier. And here, this is just a quick look, just to distinguish the two approaches of Akagi against Marquette, which is distributed based capacitor voltage balancing and sorting base of Marquette. And in this side is Marquette, and this is Akagi. You can see here the performance almost, we ramp the power from 0 to 40 megawatt. So the two performance identical, the arm current identical. And here, it's very important here. Okay, I'll go here first here. And you can see here, there's different here. You can see here in a market base, now from cycle to cycle, the number, first of all, if you see here, even though the switching frequency is 1 kilohertz, the number of switching actions per cells is a lot because capacitor voltage balancing introduce extra switching instance to maintain the capacitor voltage balancing. While in the Akagi is fixed. So the attribute of Akagi here, or the advantage of Akagi approach of a starting base, is the designs of the system is easier because the heat sink in the old system will be the same. While here you may have some issue. Some devices will operate much more than others. So so either you have to oversize the entire systems or have different heat sink for different switching devices. This is also some of the issue with the other one here. And the other point here I want to emphasize here are these two. This is here in both approach, these are identical, but here I want to emphasize one thing here. What is going on? Zoom in. Okay. And you can see here, the axis here is different than the axis here. You can see here, the axis here is from 48 to 0.5. The axis here is from 0.46 to 0.5, which means this here is equivalent to here from here. And you can see here in the MMC in general, if we add the capacitor voltage sum, or the sum, if you add all the capacitance in the upper arm, plus all the capacitance in the lower arm, you add them together, it gives you a DC components. In the top of it, there is second order harmonics, while if you subtract the capacitor voltage of the upper arm minus the capacitor voltage sum of the lower arm, you will get you'll get fundamental component. So this is the component that drive that second order harmonics in the arm of the MMC. This is the point I want to communicate from this one here. So from here we can sum up there, and this is just simple the summary of the operating conditions of these conditions. And I will go here. This is my summary for this bit, and I already explained this thing here. So in brief, just to recapture, with a Kaja with market approach, which is with sorting based capacitor voltage balancing, device operate with variable switching frequency, and therefore countermeasure is needed to restrict the range of variations. For example, we can use tolerant bands modulation approach, and there's other ways of doing it. And with the Kaja approach, which is with a Kaja approach, device operates with constant switching frequency, which simplifies the design of thermal circuits. But despite the practical the advantages and attributes of the Kaja approach, it has problems because the number of phase shift carrier you will need because the number of phase shift carrier you will need in the case of MMC with hundreds of cells become large and inseparable. So this approach become impractical in HVDC applications, but it remains suitable in MMC for medium voltage application with fewer number of cells, or if you use the HVDC converter in the form of cascaded two-level converter like ABB was using with medium voltage cells and maybe 40 cells per arm, you can still use the Kaja approach. And from here, we're going a little bit to show some sample results for the behavior of the MMC during normal and abnormal conditions. And here, this is the systems we are simulating. This is an MMC. In this case, the DC voltage is 640 and 640 pole to pole, and the rated power is 1265 MVA with active power capability of plus or minus 1200 megawatt, 400 megavar plus or minus, and the AC voltage at this site is 360, and the rest of the parameters here, and this is the rest of the parameters here. We're going to do all in that. And here also the simple illustrations. Here, this is actually part of the project we have done, where we have done a lot of modelings, and this result from 4 models, which is the first models here is 7 equivalent models of the MMC with 20 cells. Here is 350 cells, also 7 equivalents, and here switching function model with 150 cells, and here is the average model with 350 cells. You can see all these models, and this is the active power with all these 4 models looks nice as expected. This is the DC current of all these models or identical. These are the arm current of all these models, identicals as you expected. And this is the common mode current, which is the upper and lower arm. The upper and lower arm of each phase, they are summed together divided by 2, and this is here all identical. And except you can see the MMC with fewer cells show a little bit more ripple than the other one with large number of cells on average. And this is differential mode current, which is up current, which is much clearer, and here are capacitor voltages, also all similar. And here, this is the case of 3-phase to ground fault. This is the grid side voltage where the fault happened, which is solid. You can see here, this is the converter side voltage, which is well controlled with that control system we displayed earlier. And this is the zoom of this current around this point. You can see all the models likely agree. And this is the arm current. So yes, this is the arm current. You can see also the arm current well controlled. So this means why you display that one? Because this current compound this current contain the AC current and DC current all can be seen in the arm current. You can see both of them well controlled. And here is the zoom of the arm current around the fault instance. Also appear all the models almost similar. And these are the capacitor voltage as a sample of the upper arm of the capacitor voltage from all these models. Also exhibit a little bit their kind of short disturbance. And here the zoom of this you can see here, and this is the drop of the active power to zero as the voltage dropped to zero at the PCC. So the main point here, like conversion two-level converter, the average MMC can ride through symmetrical AC fault with three-phase AC output currents well controlled and restrained. So the current stress in switching devices and passive elements are tightly controlled. A single phase fault, and here in negative sequence current controller, we suppress negative sequence current to zero, so to maintain the current at the converter side to be balanced. As you can see here, this is the current at the grid side, which include negative and zero sequence because of the ground fault, and this one the current at the converter side. And you can see here the current converter side well balanced, and these are the zoom of these two plots. So all the models actually nicely agree. And here also these are also the upper arm currents, and this is the zoom of the upper arm currents around the instance of the fault inception. And these are the capacitor voltages, and this is the zoom of the capacitor voltages around the fault inceptions. All the model agree, and also everything is under control. And here, and this is a DC current of DC, and you can see here, you can see there is differences. The one with 20 cells exhibit slightly some differences, but that difference only appear in DC current. And also, if you look closely, that also appears also to some level in the arm current. So the number of cells have minimum impact in the accuracy of the results. This is the conclusion I want to say from here. Also here, unlike the conventional two-level converter, the average MMC can ride through a symmetrical AC fault with balance and control three-phase AC current and ripple-free this bit, a ripple-free DC voltage. Because in two-level converter, you only have 1 degree of freedoms. Either you can keep AC current balance, or you can keep a DC current ripple-free with unbalanced AC current. But because in the MMC we have two loop, common mode loop, and differential loop, so actually we have extra degree of freedom to have to achieve two objectives at system level. And also the current stress in switching devices and passive devices are tightly controlled, as we have seen from the results. And here is the pole-to-pole DC short circuit fault. And also here we have done, but here we change it slightly. I think the number of cells. Here we have 20 cell detailed switch model. Of 20 cells, 7 equivalent models. We have 256 7 equivalent models. We have 256 switching function models. And these are the operating conditions. I will not dwell on that. And here you can see here, this is the DC voltages. You can see here the DC voltage of MMC with fewer number of cells show slightly more ripple because of the switching error, because if you have there, so with 20 cells, the cell voltage is so bigger, so the error and synthesis of DC voltage is slightly bigger, so you will see that ripple in the DC voltage you can see here. And you can see here, this is, and this is the DC current, you can see likely similar, and you can see also there is some differences in the capacitor voltages. And these are the amp currents. You can see also some minor differences in the amp current, but insignificant, I can say that. So in summary, we can say all the models have exhibited similar performances with worst case error of less than 1%. A number of cells have no bearings on the accuracy of the AC side waveforms, but however, the switching functions MTV with reduced number of cells and average there exhibit similar error of less than 1% in peaks of the cell capacitor voltage and amp current. So we can say all the models have consistently exhibited closely matched result in normal operations, AC fault and DC fault. Sorry. And let's go from here to full bridge and mixed cell MMC. I'll go straight forward. And here, this is also a test system. I will not do much here. And here, first is a mixed cell. And here, this is a simulation scenario. We have two simulations here because all the previous one was similar to the other one. I just want to show the cases which is different than the average MMC. And we can see from here, in the first case, we have pole-to-pole DC short circuit fault, and the other one is pole-to-ground. Pole-to-ground fault. And here in the pole-to-pole DC fault, we can see here the DC voltage drop from 640 to 0. But in this case, we enable the fault control of the mixed cell MMC, and the mixed cell MMC here, what does it mean? Is the MMC here, we have the half bridge, but what we have done here, the 50% of the cell here are full bridge, and the other 50% are half bridge, and this repeated in all. So 50% of the converter cells half bridge, and the other one are full bridge. And we added fault control here. In this, you can see here the DC voltage drop to 0, but you can see here the DC current is controlled to 0 quickly. And importantly here, you can see the amp current also remain well controlled. And I'll show you why you have some current in the amp current. And here, and these are amp capacitor voltages. You can see here everything is under control. And you can see here, even though the DC voltage was collapsed to 0, the reactive power is still, we can still control reactive power at the rated with brief disturbance just around the instance of the fault. So this clearly, and the active power dropped to 0 because the DC voltage dropped to 0, and the VDC times IDC equal to DC power equal to active power. Since the VDC dropped to 0, so the active power has to go to 0. This is why we drop the active power to 0, while we return the control to we return to source the rated reactive power as it was in normal conditions, and with control grid current still. So the main point here, we can say the mixed cell MMC can block or actively control pole-to-pole DC faults as full bridge MMC, and also during pole-to-pole DC fault, the mixed cell MMC can provide reactive power as shown in here as a STATCOM. And here is the pole to ground. But here I want to demonstrate this very important feature we call pole restraining. You can see here at this point a pole to ground fault happened, and here this is the plot for the positive pole to ground and negative pole to ground, and you can see at the fault happened at the negative pole. So the negative pole dropped to 0, and the fault shifting happened because because of the asymmetric nature of the converter. So the healthy pole jump to full VDC. So if you allow that to happen for a long time, the DC couple will explode. So what we have done here, we instructed the converter to reduce the DC voltage to half. And you can see here now the fault still exists, but now we're operating with VDC at half. But before we activate these actions, we have to reduce the active power to half. So from here we go from 1200 megawatt to 600 megawatt. And I think maybe this is in the other plot. Yeah, and you can see here and the DC current. So in this case, with the 50% of DC voltage, and we can deliver like 50% of the active power with the rated current, as you can see from this plot here. And you can see all the other things, the grid current remained like nothing happened. And these are the arm current. We can look like that. And here are the arm current. Yeah. And also in summary, we can say the mixed cell AMC can continue operate during pole to ground DC fault and prevent excessive overvoltage in the healthy DC pole. Thus, the risk of the sensor failure is reduced. And during pole to pole, during pole to ground DC fault, the mixed cells MMC can transmit 50% of the rated power at 50% of DC voltage with 100% of the rated current. And we go here in the last scenario here of the full bridge MMC. I will not go here. This is just the summary of the operating conditions. And here also have a couple models. We have P-SCAD models. PA is average model in the P-SCAD. And this is the P-SCAD switching function model. This is P-SCAD 7 equivalent model. Real-time simulation RTDS switching function model. RTDS average model. And you can see here, to demonstrate actually a DC voltage reversal. What happened here, initially we operate normally, and at this point we reversed a DC voltage from 640 to minus 640. But before doing that, initially we reduced the active power to 0. And then we perform the DC voltage reversal, and you can see here, and these are the plot, and this is the voltage of the positive pole and the voltage of the negative pole. You can see at this point they become reverse when you reverse the DC voltage there. And you can see here, because we maintain the power flow constant with the change of DC voltage, the current, DC current polarity has to change. This means if we kept the DC current to be fixed, positive or negative, then the active power will change. So this example clearly shows actually by in the full bridge MMC, we can change the power flow either by DC voltage change or by change of polarity of DC voltage or change of the polarity of DC current, while the reactive power remain unaffected over the entire period. And this also here is the voltage across the upper arm, and you can see here when we operate with positive DC voltage, the entire arm voltage between 0 and VDC, while when we operate with negative voltage, the arm voltage shift down, as explained earlier in the initial diagram that defined the control range of the MMC. And this is the zoom plot of the arm voltage around this point here. You can see here we become completely down in the negative part. And here is the arm current. And you can see here the capacitor voltage remain unaffected and positive, like nothing happened here. So in brief, we can summarize. We can say beside DC fault blocking and active control of pole-to-pole DC fault, the full bridge is a representative of the MMC with symmetrical cells, which extend the VSC control range beyond that of the mixed cells MMC. For example, which is, as we just show here, bipolar DC voltage operations. And also, and this is the second point here, the full bridge can reverse active power directions by change of DC current of DC voltage polarity. Therefore, it is well suited for operation alongside the LCC in potential transnational DC grid. And from here now, this is topology we have developed in a satellite.
Great, you have 5 minutes time.
Oh, okay, then it's fine. Okay, then I will stop here then, yeah. Okay, then.
You can conclude, please.
Okay, then. Okay, then. If this case, then I'm up to here. I'll finish here. Yeah. Okay, then. Yeah. If there's any question, I can take question. Yeah.
It's almost 5 minutes since you started. Okay, if there is any questions from the audience, Grain is ready to respond. Abdurkhani, you can ask one question. Professor.
He's not there.
No, he's not there. He's in. Maybe he's not listening to us. Tankari, can you ask one question to Gray?
We will order coffee. Who want ask question?
Is Rosario inside? No.
I think I think they left maybe, yeah.
Yeah, I think. Graham, may I ask one question? Maybe I misunderstood your explanations. Okay. I remember that we were talking about the second order harmonics. As yes. I remember, if the system is in balance, second order harmonics are diminished by itself and then do not affect the loss. Is that correct?
Can you repeat the question?
I mean, is your second order harmonics affecting the loss in your system?
Yes. No, because here, okay, just a minute. Let me go back here. Okay. Okay, maybe a little.
So second order harmonics are very high, and if it is affecting.
Yeah. Okay, just a minute. I think I can explain to you. Let me, in the basic here, I think maybe slightly up here. Yes, it's here. Okay, I will go here. Okay, you can see here. This is here actually. Let me zoom here. In this figure, okay. This is the inherent second order harmonic component in the MMC. You can see here in the black line here. You can see here the DC in the top of second order harmonics. But this is why in this case, maybe it's clearer in this case. In this case, we aspire to eliminate that second order harmonics here. So this one, yes.
Blue one is diminished by the green one, I think. Eh?
Pardon?
The harmonic in blue color is reduced by the green color. Is that correct?
No. In this case here, you can see here the upper and lower arm Okay, just a minute. Let me go back here first. I think I'll go back here. Let me zoom in. If you see here, in this case here, this is the upper and lower arm. This pink and this blue as the arm and the upper arm. This current contains second order harmonics.
Okay.
Okay. In this case, second harmonic will increase the losses, and you will need bigger capacitor to maintain the ripple in the capacitor voltage lower. And so, to avoid this outcome, we added extra controller just to suppress that second order harmonics here. In this case, and that also actually help in the, and this controller also help if you go in the, I want to go in this case of single phase fault. In single phase fault, typically, if you have two-level converter, you have 1 degree of freedoms. You have options. If you maintain the output current, the output current balance like that, you will see second order harmonic current in your arm and also in the DC voltage. But in the MMC, because we have two loop, we have common mode loop and we have differential mode loop. These two loops allow us actually to do two objectives. So we can maintain the current balance here, and also if you go here and you can keep I think here, and you can see here a DC current is clean from second order harmonics.
All right.
Yeah.
All right. Thank you, Gray. Thank you. Any other question, please?
I think people left maybe, huh?
No. I can share the certificate now with you, and let me see how can I share my screen with you.
Okay, then I stop sharing then.
Yeah.
I gave you back the control, yeah.
Okay, do you see it now?
Thank you so much, yeah?
Send your mail as well, Gray.
Awesome. Oh, thank you so much. Yeah.
Thank you very much for your great tutorial, and it was very successful. Although it was end of today, but we have seen more than 30 people are listening to your tutorial, so it's a very important number. Thank you again, and see you tomorrow. Is there anybody else asking any questions for today's presentations, please? If you have any questions, you can ask now, or you can write me later on. I see the Rosario is there. We were looking for you, Rosario, to ask the question, but you were not there.
I was in the lab a minute. Now, what is the plan? Now we have finished the today conference?
We have already finished and given the certificate to Gray. And we are about to close the session and then go and have a rest and start the morning tomorrow.
Where is the
At what time tomorrow morning we will see each other?
It starts at 10 o'clock in the morning.
10 o'clock in the morning, perfect.
But if you want, we can drink something, water, coffee in here.
Some water.
Yeah, water.
Where is the dinner?
Today in Palermo, it's very, very hot.
Very hot, yes.
30 degrees.
I imagine it. But we missed Palermo.
I hope that you will come soon, because not only for the weather, but I hope too that perhaps in Glasgow we can meet each other. I don't know up to now.
Yes.
Grain took me to a very nice restaurant for the dinner in Glasgow. I hope we will find a good restaurant in Palermo as well.
But it's
Yes,
not good.
of course.
But it's not good for Professor, because actually, because he's Italian, and come to Glasgow, also to Italian restaurant.
Yes.
We will try if they are good.
But finally we went another one.
Yes.
So,
Yeah.
my friend Professor Bulbul, and we will try to understand if they are good. Okay,
Yeah.
Ali?
Okay, thank you. Yeah.
Okay.
Perfect. Very, very, very good.
Okay, thank you.
Okay. I would like to thank you to all attendees and all colleagues and friends today, being patient and listening to all presentations. Professor Kurukawa, you are here. It is midnight in Japan, but you are still following the tutorials.
Yes, but we know that Furio
Are you in Paris?
go to bed very late in the night.
Yeah. 1 o'clock midnight.
Midnight, 4 o'clock midnight.
Yes. Yeah.
So that means you will not sleep till the next session tomorrow.
We hope that in Glasgow there will be some good place to have some drinks with food.
Yes, definitely. Definitely. Huh? If you come here, we'll treat you with something special.
But is there the possibility to drink unalcoholic drinks? Alcoholic and unalcoholic.
You can find everything in Glasgow.
Perfect. So we can bring with us Alil and Ilami. Perfect.
Okay,
Rosario.
Yes.
Grain booked a restaurant, Italian restaurant, for the dinner together when I visited there. And
In Glasgow?
at that restaurant, it was very full. And they said you are in the queue and then you can come after more than 1 hour. So we went another place.
It means that it was a good restaurant. It was very full.
Yes, it was a good restaurant.
So we have to try.
So hopefully this pandemic will be over soon and then we can go Glasgow all together.
It's my dream to be there with you, with all of us. With all the family. It's a long time that we don't embrace each together, and so now I need some energy from the family.
Glasgow is a very good city for shopping. Comparing to London, it is very
cheap. Glasgow is very, very beautiful.
Yeah.
Even if it's a long time that I haven't been there. So I am curious to see what are the changes.
Yeah, I think Glasgow actually is for shopping is very good. Also cheap. It was cheap. Yeah. Compared to Paris and Milan, it's much cheaper. Yeah.
Okay, but the important thing is to stay together, not to go shopping.
Yeah, no problem.
Perhaps for Ilami it's important shopping for his kids.
Yeah. I think they can go themselves. They don't need me.
They go alone with the father.
Yeah.
But don't worry, even in Glasgow, the godfather has some friends. So they are safe.
Yeah. I know Glasgow is very beautiful place and very nice to visit it actually. We have very nice friends there, and I know the Icsmartgrid University for a long time. So it's a very old university and very powerful one. I know their new buildings, and it's built recently. I visited Grain's office in the new building.
Very, very good. But I saw very few, for few minutes, Sharef and Ramazan. Where are they?
Ramazan went to another meeting.
Ah.
Sharef just called me that he is very busy. He went to another meeting and he is very tired. So he will be with us in the morning.
Yes, because we used him. We used Sharef for a conference in Palermo. We, of course, we would have some, but you say, I am not in that conference because I asked them to postpone the conference after Icsmartgrid. They didn't agree, and so I am not in that team. In that team, there is Fabio, that is, of course, thanking you for all things and say to you bye and see each other in Glasgow.
Okay.
Soon.
Where is Fabio?
Fabio is working in another conference now in these days.
Will he with us tomorrow?
I think that tomorrow he will be with us.
Okay.
I will bring it with me.
Okay.
How about Ciro?
Ciro, at the moment, is not coming here at the university. He is very well, but I hope tomorrow we will see him too.
Connect.
Of course, Ilami will invite him. I will send a WhatsApp message, and so
Please
he
give
can.
him and then ask him to join us via internet.
Perfect.
We missed him. Ciro is very important.
And
He was playing
he
guitar.
told me that he want to stay with you and sing songs for you. You know,
Yeah, Turkish music.
Turkish music, of course.
He has a very, very good album.
Turkish music, like we did in Brasov.
Yes.
Nothing Brashov. Do you remember?
Very beautiful.
Rosario, do you remember the Milwaukee?
Yes, of course, Milwaukee with the guitar, and we invited a lot of people to join us. It was a very wonderful night in Milwaukee.
It was a great collaboration of Turkish and the Italians.
Great collaboration, but we always stay very well, and I'm sure that in Glasgow we will stay very well too, and we will have the facility to stay when all the event finished. We can stay together and have some music from Ciro and some songs, Italian songs for us, only for us, of course, for friends.
Why
for
not?
You're most welcome. And actually,
he can play.
Friday, you have to, you say, to find for us a guitar.
Yeah. Do
you
agree?
Galadina, for the Galadina.
Yes. Yes.
So we can make some funny after the Galadina.
Yes, sure.
Together.
Sure.
That is very important to feel our feeling when we are together. That is very important to let the other people understand what is our group.
Yeah.
But Ilami,
yes,
have
please.
you told to Grain that why you are named the Spider?
Name?
Why your nickname is the Spider? For your net.
I didn't ask.
No. We have time to explain.
Okay.
Okay, so have a nice relax now, and we will see tomorrow at 10 o'clock.
I'll see you tomorrow. Yeah. I'll see you tomorrow.
Have a very nice night.
Thank you so much. Yeah. Thank you so much. Yeah. Thank you. Thank you.
See you tomorrow.
I'll see you tomorrow.
Professor.
Good night. Good night.
Professor Kurokaro.
Good night.
Good night. Yeah.
Furio.
Yes, good
Hi.
night.
Would you start the online welcome party?
Yes, welcome party.
Sure.
Yeah.
We need a very good welcome party.
Massimo, see you tomorrow.
See you
See you
tomorrow.
Professor.
There are other guests, but they don't talk. I don't understand why.
Professor
Perhaps
Kurukova.
they are working. Of course, they are working in some other rooms, and so they don't know that we have finished.
Okay.
Professor Kurukova.
Yeah.
We have belly dancing in the night. Are you coming?
Okay.
Oh, Ren, you have to know that Furio is a very well, a good dancer.
I know. I know that. Okay, we meet in the 1 hours later in the Paris metro. Okay.
Okay.
Okay. Okay.
So this night we will go to the nightclub
Okay.
in Paris.
Have a
Good
good
night,
rest.
all of you.
Good night.
Rain.
Yeah.
Thank you.
Goodbye.
Bye.
Bye.
Good night.